Hey everybody, before we get into this, let's talk about a useful property of factorial. Now, very familiar object mathematically. N factorial just means 1 times 2 times 3 all the way out to n. But you can unfold it in this fashion. You can write it as n times n minus 1. And you can, this part of it can go on indefinitely, you know. But wait, that should be, sorry. Gotta learn to talk. So n minus 1, n minus 2. Now I'll just arbitrarily stop at 2, but this is times n minus 3 factorial. Totally consistent with the definition of factorial. Okay, so that'll get used. And also a result that's very, very well known, maybe the result, kind of the central result in number theory, at least elementary number theory, is a result called Wilson's theorem that states this. P minus 1 factorial is congruent to negative 1. And I'll include my P here. P is a prime number. Okay. The standard proof for it doesn't work for the even prime, but it's easy to verify for 2 that it works. You would get 1 factorial, which is 1 minus a negative 1 is a multiple of 2, namely 2 itself. Okay, so let's see how we carry on here using these 2 results. So I used, this is a statement of Wilson's theorem right here. P minus 1 factorial is congruent to minus 1. And I should be writing, I just didn't have quite the room here. I'll put mod P right here. So nothing more than restating Wilson's theorem right here, folks, Wilson's theorem. And we went out this far because we just needed to get it to P minus 4 factorial. Okay, so we're looking for the prime modulus such that P minus 4 factorial is congruent to this number 175. Okay, now a very, very useful fact here, and this, it took me a while to get used to this, but P is congruent to 0 mod P. Right? P is congruent to 0 modulo P. P minus 0 is P. Okay? So any multiple of P is congruent to 0 mod P. So that's what happens exactly on this this is just the definition of factorial going from here to here, right? And so then I replace P with 0 here and here, and you get minus 1, minus 2, minus 3, minus 1. Again, very, very straightforward. Now, this all multiplies out to negative 6. Then we have minus 6 times P minus 4 factorial is congruent to minus 1. Now, I did want to show you one thing here that's fairly interesting. Some people wonder about canceling minus signs. Well, remember, congruence deals more with arithmetic. And let me tell you what I mean by that. I'll use P here, and I won't write out these complete objects here. But P would divide... let me put it in parentheses, minus 6, or I'll just call it minus a, just don't have to write all that out, guys. Okay, so make this whole piece right here, this is just your minus a object right here. Now when you subtract, you get plus 1 here. So that's what this statement literally says, right? But notice that you could rewrite this, in other words, P divides minus a plus 1 means the same thing as P divides 1 minus a. And so you can see that you can cancel the minus signs for that reason. In other words, let me just do it like this. I'll do if and only if. P divides a minus 1. Okay, and that's certainly clear. These are additive inverses of each other. And so this statement down here would be equivalent to just the minus signs canceling, okay, which is what I wrote down right here, folks. I should have put all this work right here. But yeah, you see this division statement corresponds exactly to this statement, right? And when I say division, that's literally what this means. congruence is based on divisibility, which is a partial order. Okay, so you don't cancel the minus signs in the same sense that you would with real numbers. It's just a property of the divisibility. And maybe I should say this: P divides, if P divides A, it necessarily divides. Let me just do if and only if. It helped me because I remember when I was first learning this stuff, I was going, man, is it really, I mean, the same kind of thing is true, but for different reasons, I guess, is a way of putting it. Okay. Okay. These two statements are why this statement right here is the reason why we can jump from this step to this step. That is, cancel the minus signs. Okay. Now, maybe you didn't have that much trouble with it, and that was a waste of time for you, but I thought it was a useful thing to say. Now, so we're given that p minus 4 factorial, where are we at here? Okay. We're given this right here that p minus 4 factorial is congruent to 175. So what we can do right now is write down 6 times 175 right here. 6 times 175, right? Because literally, it's a given. It's an equality. We're given that p minus 4 factorial is congruent to 175. It's the same as equal. And we're looking for the p that gets that done. So we have this is congruent to. We have this is congruent to 1 mod p. Okay, now what p would do that? Well, we got to know what 6 times 175 is. 6 times 175, 14, 12. Is it 1050, right, folks? I think. I'm getting slow. Okay, 6 times 170, right, would be. Yeah, that does it. That does it, right, folks? Okay, I think that's correct. Okay, I'll trust myself on that. Okay, so this is congruent to 1 mod p. And again, we're trying to find the p that gets the job done. Okay, and so that would imply that p is equal to 1049. And y'all, you notice there's no reason to really check this because we started with Wilson's theorem. We started with Wilson's theorem. And it can't be any number bigger because it would have to be a multiple p and it wouldn't be a prime, right? So that's kind of cool. So this is the answer I got, folks, 1049. Okay. I'm still double checking the arithmetic right here. 6, 420, yeah, then plus another 30, right? So that is 1050. So I got, and some of you might be thinking, really, you don't have to check? No, you don't. You can check all the square roots. You would have to go up to the 31 maybe. 37 squared is much bigger than 1049, right? So you'd have to check the prime divisors 31 and below, okay? And you could quickly find out that 1049 is a prime. But notice that we did start with this result called Wilson's theorem. What's going on here? We started with the result called Wilson's theorem. And Wilson's theorem is necessary and sufficient conditions for primes. That's kind of an interesting result. It's not very useful because the numbers get big so fast. But this is necessary and sufficient for a number to be a prime number. So we started with it and reached this number 1049, which necessarily is going to be a prime. Okay, so that is the answer. P is equal to 1049. Now, just is there anything else to say here? Had it not, let's say I'd given you a number here that hadn't been carefully calculated, this just wouldn't turn out to be an integer here. It would be false. You would probably get rational numbers down here during the computation. Okay, so anyway, it's P is equal to 1049. All right, folks. Thanks for viewing.